Today we are talking about L'Hôpital's rule. Now it looks like it says La Hospital, but it is not. It's pronounced L'Hôpital. And L'Hôpital's rule is used to evaluate limits. The specific thing about these limits is they have to have an indeterminate form. And that's a form of an answer where we cannot determine what the value is. So those indeterminate forms involve infinity over infinity. Although it looks like it should perhaps be 1, it's not. 0 over 0 is another one. No idea what that means. 1 raised to the infinity, 0 raised to the 0, infinity raised to 0, and the difference between infinity and infinity. So before we can use L'Hôpital's rule, we have to get the limit into one of the fractional indeterminate forms. So when you take the limit and you get one of these two results, that means we can use L'Hôpital's rule. So here's L'Hôpital's rule written out, and basically what we need to know is if we have this limit that we're trying to find, so this would be our limit, and we get an indeterminate form when we actually evaluate that limit, then what we can do is take the same limit as x approaches the same value. However, instead of using g on the top, we use the derivative of g on the top. Instead of using h on the bottom, we use the derivative of h on the bottom. So let's go ahead and just do this first example. So the first thing I need to do is evaluate this limit and see what I get, because I have to get an indeterminate form before I can use L'Hôpital's. Now I don't usually like to use an equal sign, I use kind of an arrow sign because I'm looking for an indeterminate form. So the first thing I do is I plug in, let's see what we get. And on the top I end up with a 0, on the bottom I end up with a 0, and this is an indeterminate form. So once I have an indeterminate form, I can use L'Hôpital. So once I get started, I'm now going to do the limit as x approaches 1 of the derivative of the top all over the derivative of the bottom. And again, it's not a quotient rule, it's the derivative of the top and the derivative of the bottom. So let's go ahead and see what we get when we do this. Now we have the limit as x approaches 1 of 2x plus 2 on the top, and the derivative natural log of x is 1 over x on the bottom. And let's see what we get now when we evaluate. So when I evaluate this, I get 2 plus 2 on the top, and I get 1 on the bottom, which gives me 4. So here is the limit value by using L'Hôpital's rule. So let's look at this next example. Find the horizontal asymptote for this function. Now, I'm guessing that at a glance you actually already know the horizontal asymptote for this function because you were taught a trick as to what eventually is going to happen. And maybe not a trick, but it was a pattern that would always happen when you used other techniques for evaluating this limit. But now we're going to look at this limit using L'Hôpital's. So if I were to take the limit as x approaches infinity of this, 5x cubed minus 9x squared plus 10 over 2x cubed plus 7x minus 4, and I were to plug in infinity, this thing would approach infinity over infinity. And of course, that's an indeterminate form, which means we can use L'Hôpital. So let's try that. So now we take the limit as x approaches infinity of the derivative of the top, 15x squared minus 18x over 6x squared plus 7. And let's go ahead and evaluate what we get now. And when I plug in infinity on the top, I still get infinity. When I plug in infinity on the bottom, I still get infinity, which is another indeterminate form, which means to use L'Hopital's again. And I can use L'Hopital's as many times as I need to. So let's go ahead and do it again. Now I have the limit as x approaches infinity of 30x minus 18 over 12x. So I evaluate again, plug in my infinity, and I get infinity on the top, I get infinity on the bottom. I have another indeterminate form, which means L'Hopital's again. And again, I can just, as long as I get an indeterminate form, I can keep using L'Hopital's rule. So now I have the limit as x approaches infinity of 30 divided by 12, which is just 30 divided by 12, but I can simplify that to 5 over 2, which means the horizontal asymptote is this y equals 5 halves. And again, from looking at this problem, I know that you recognize that the asymptote should have been 5 over halves. You take the coefficient of the highest exponent on the top and the coefficient of the highest exponent on the bottom. If the exponents are the same, then the horizontal asymptote will just be those two coefficients. So again, you've learned how to do this a different way, typically by dividing by the highest exponent of x in the denominator. Every single term gets divided by that, but L'Hopital's rule will get us the same result. So moving on to example 3, let's see what we have. So let's see if we try to evaluate this. We have infinity times e to the negative infinity, which is times 0. E to the negative infinity will be 0. So this is an indeterminate form, which means I can use L'Hopital's. But before I can use L'Hopital's, I need to get a fraction. And our fraction should be infinity over infinity, or 0 over 0. So let's rewrite this thing first. Limit as x approaches infinity. And this one's actually simple to get into a fraction because e raised to the negative x is the same as e to the x in the denominator. So let's check and see what I get when I evaluate this. Now I get an infinity on top and I get an infinity on the bottom, which is an indeterminate form, which means I can use L'Hopital's. So let's use L'Hopital's, and I now have the limit as x approaches infinity of 2x over e to the x. Let's evaluate and see where we are. When I plug infinity, I get infinity on the top, and I get infinity on the bottom, which is another indeterminate form, which means I can use L'Hopital's. And let's see what we get when we do our next L'Hopital's. On the top I get a 2, on the bottom I get an e to the x, and that is, the top stays 2 and the bottom is going towards infinity, which means this limit is equal to 0. So the limit as x approaches infinity of x squared e to the negative x is 0. So for the next one, this is one that I would like for you to try. So go ahead and work this one, and when you're finished, I'll have the solution up there. So go ahead and pause the video now, please. So here's my solution. I get that that limit is 0. Go ahead and pause the video if you need to take a look at my work. On to example 4. This one is a different style because now we have a variable in our exponent. I know this is kind of difficult to read, but what this is saying is the limit as x approaches 1 of x raised to the 1 over 1 minus x. So this is what we have. And so what we need is to evaluate what this is. So first of all, we have 1 raised to the 1 over 0, which is infinity, which is an indeterminate form. So, but I need to make it into a fraction before I can use L'Hopital's, and I can't use L'Hopital's right now because I don't have a fraction. So I have a little bit of a dilemma here. What I'm going to do though is I'm going to treat it like logarithmic differentiation. So I'm going to start with writing that L is the limit as x approaches 1 of x raised to 1 over 1 minus x. So first I need to write an equation. The next thing that I need to do is take the natural log of each side. So I'm going to take the natural log of each side of my equation. And from here, I'm going to go ahead and move my natural log on the right side so that it's within my limit. That shouldn't change anything. If I take the natural log of the limit value, that should be the same as the limit of the natural log of the value. So doing that should be okay. Now I'm going to use my log rules to simplify this. And I'm going to bring that exponent down. So I have 1 over 1 minus x times the natural log of x. And at this point, I now can make this into a fraction. And again, that's my goal right now, is to make this into a fraction so that I can use L'Hopital's if it applies. So let's give a little check and see if it applies. The natural log of 1 is 0. 1 minus 1 is 0. Now I have an indeterminate form, which means I can use L'Hopital's. So from here, I'll use my L'Hopital's once, and the derivative of the top is 1 over x. The derivative at the bottom is a negative 1. And now I believe I can evaluate that. And when I evaluate, I get the natural log of L is equal to, sorry, I know the limit now. I can just plug in my 1, and that gives me negative 1. So I now know the natural log of L is negative 1. Well, how do I get what L actually is? Well, what we're going to do is now undo the fact that we took the natural log of both sides by raising both sides to e raised to each side of my equation. So now I have e raised to the natural log of L, and e raised to the natural log of L is just L, and e raised to negative 1 is e to the negative 1, or 1 over e. So let's rewrite what my actual answer is. So the limit as x approaches 1 of x raised to the 1 over 1 minus x is 1 over e, or e raised to the negative 1, whichever you prefer. Okay, so I think we have one more left, and I believe this is one that I would like for you to try. So you're going to do this exactly the way we just did our last example. I'm taking the natural log of both sides, evaluating the limit after you get a fraction, make it a L'Hopital's rule, and be sure and take e to the both sides. So right now I'd like you to pause the video and do this problem. Here is my solution. I get that that limit is 1. My work goes on the left side, and when I run out of space, it goes follow the blue arrow to the right side. So if you need to take a look at my solution, please pause the video. Be sure and bring any questions you have to class, and I hope you have a wonderful evening.